Hey, welcome to another video. Now that we've talked about the library functions and the basic functions I asked you to memorize, hope you memorized them, especially with their key points and what they look like, we're going to take them and we're going to graph with these things called transformations. So what transformations do is has you look at a function and determine just based on the operation that's happening with it, what the graph is going to affect, how it's going to affect one of these basic graph shapes in the library functions, whether it moves it up or down or left or right or stretches, compresses it, reflects it, all these sort of things that transformations do. Why that's important, why we want to know that. We don't want to have to plug in points or evaluate a whole bunch of different points in a function every time because for a number of reasons. Number one, we might miss some very key features of a graph. What if you don't plug in the right points? Or, man, it takes a tremendous amount of time. And for these graphs that continue forever, like trigonometric functions, it's really useful to understand what in the world these operations are doing to the graph of your function. That's why we start right now with these things called transformations. We're not going to talk about trigonometric functions now, but later on we will, and we'll revisit all of this stuff. And if I can teach you what shifts a graph up and down, what shifts a graph left and right, what stretches it, compresses it, both horizontally and vertically, then when we get to trigonometry, it's going to be a piece of cake to graph the, not a piece of cake, but a lot easier to graph them. So really we want to get a feel for what these graphs are doing by just looking at the functions themselves and the operations that are taking place. The things you need to know in order to do this are, number one, what does an x squared graph look like? What does an absolute value of x graph look like? What are the key points there? And then I'm going to teach you how to transform them. So let's start right away. We're going to talk about what a vertical shift is. Now, please don't just memorize this. Understand what's taking place and why in the world adding or subtracting outside of your function, so like this plus 3, why that would be a shift up or down, vertical shift on the y-axis. So I want you to take a look at it. Let's imagine that you have, wait a minute, we understand this. We know that x is our input. So stick with me here. If I had an x value and I plug it into a function, the function's value is an output for that whatever that x value is. So it says take an input, plug it into a function, you get an output. Now this right here, this f of x, this is the output for your graph. What if you took the output value, f of x is an output value, and you added something to it, a constant. So you just added a number to an output. What's that going to do? Is that going to affect the input that you plugged in? No. Is it going to affect the output value of your function? Yes. What this says is if you have an output value, or you take a function's output value and you just add to it, or you take an output value and you subtract from it, what's going to happen? It's not going to move it left or right. That would be an input idea. That's not affecting the input. I haven't taken x and affected the input. It can't move it on the input axis. This says take your output, add or subtract. Take your output, that's an output axis idea, and add or subtract to or from it. Adding to an output's value is going to change the output and make it taller, or will make it higher. It's going to take that and shift it vertically upward. Taking an output value and subtracting from it is going to take the output of a function and move it lower. So these are going to give us what's called a vertical shift or a vertical transformation. It's going to shift it up for plus and minus for down. That's got to make sense. You got to see it. You got to see that our input would go into a function. This is the output of a function, and now I would just add to every single one of the outputs. That would be the same value I'm adding for every one of the outputs. You can take the graph shape, that's going to move it up. Or take the graph shape and move it down. That's where this comes from. So when I take a function value and I add after the function, outside the parentheses, after everything's been accomplished, and then I take the output value and add to it, that's a shift up. Or if I subtract, that's a shift down. One thing to really focus on here, this is not affecting the input. It says take a value, plug it into your function, yeah. Then after you've plugged it in, after the parentheses are over, after you've squared stuff or cubed it or square rooted or absolute valued it, outside of that, after the function, you'd have an output value, wouldn't you? Now add to that. Oh, I'm taking the output value and I'm adding to it. Or I'm taking the output value and I'm subtracting from it. That's why this shifts up or down, but not left and right. It's affecting the output only. Input does not change, output does change, and it's shifting it. units above or units below. That's what we're talking about here. So when we talk about x squared plus 3, I'm going to give you a very specific way on how I want you to graph these. It's not going to be in any textbook that I know of, because I made it up. But as far as I know, maybe not. But here's the way that I do this. Number one, I identify what my basic graph shape is. It's going to be in one of the library functions that you just talked about in the last video. So when I look at this, I go, okay, the key basic function here is x squared. What are your key points for that function? Don't be overthinking it with the plus 3 right now. Just think, what's my basic graph shape? X squared. What are my key points? You go, okay, my key points, it's very important. My key points are 1, 1, 0, 0, and because it's based on an even function, -1, +1. That is what I wanted you to remember from the last video. Firstly, what the graph's shape is. This is a parabola. Secondly, what my key points are. 1, 1, 0, 0, -1, +1. I need that to be there. Now that we have the basic graph shape in our heads, we know it's a parabola, we know what our key points are, that's them, we're going to look at what the plus 3 does. So we think, okay, this is a parabola, and this says take the output values. So you plugged in a number, right? You squared it, that's an output value, and now add 3 to it. Adding 3 to the output value is going to be a shift up 3. So I'm going to circle that. I'm going to say that this plus 3, that means I would take my original basic graph shape, my parabola, and I would shift every one of those values, those output values up. I have a very kind of neat way to do this graphically. So here's what we're going to do. If we're going to shift every single value of this graph up 3, not left or right, we're going to leave that alone, but up 3, here's what I'm going to have us do. I'm going to say, you know what we could do? Instead of graphing this on the original XY axis, what if we pretended that we shifted the X axis up 3? What if we pretended we didn't shift the y-axis at all? Why not? I'm not moving left or right. I'm staying right where my input is. This shift is not affecting my input, it's affecting my output. So I'm going to pretend my shift up moves my x-axis up. It shifted the whole graph up. It has not shifted my y-axis up left or right at all. So that's staying there. I want to make a couple key comments about this. When I'm doing this, I'm not really shifting the x-axis up. We're just kind of pretending. We're giving ourselves a graphic organizer so that we can say, you know what, this parabola is all shifting up 3 units. If the whole thing's shifting up 3 units, let's shift our axes. Let's shift up 3 units, and let's shift left or right no units. Let's leave that alone. But if I do that, then what I can do is take the key points of our basic graph shape, and if I graph them from my new XY axis, if I say, all right, this graph would always have 1, 1, right? Well, yeah, but now I shifted it up 3 spots, 3 units. Using the same scale, let's plot 1, 1. Using the same scale, let's plot 0, 0 from my new XY axis. Let's plot -1, 1. On the same scale. What that's going to do, if I got my scale right, which I didn't, what that's going to do, that's going to allow us to graph the parabola that we know this graph gives us, but it's going to allow us to graph it in the correct spot. So the whole idea is identify what your basic graph shape is. Got it. Identify what your key points are that you should have down. Understanding why I taught you hey, even has the 1, 1, 0, 0, -1, +1, and odd has the -1, -1, will make it a lot nicer. You go, that's even, it's got these as key points. Great, I know what the shape is, I know what the key points are. I also understand that up 3, that plus 3 says, I'm taking and shifting this graph up 3 spots. If we pretend our x-axis shifts up, and if we pretend our y-axis doesn't shift at all, that gives me this new place on which I can graph my key points. Now please understand, this is not really on your graph. It's not really there. It's not really the x-axis. It just gives us a way for us to graph it nice. And from our new xy axis, we can graph 1, 1, 0, 0, -1, +1. Are the points 1, 1, 0, 0, and -1, 1 on your graph? No. The real points are 1, 4, 0, 3, -1, 4. Why? Because you took these output values and you added 3 to them. That's what happened. That's what's going on. It's just nice to be able to graph it that way. I hope that makes sense. I hope you're seeing why adding a value at the end of your function is shifting up, outside parentheses, outside absolute value, outside all the function stuff, and minus is down. You're taking the output value, you're adding or subtracting respectively. One way we can show that is to shift our x and our y axis, give a new xy axis, not really there, and then plot our key points. Works very nicely. Now let's move on a little bit. What about a horizontal shift? Well, wait a minute. A vertical shift, what that did was it took an output value and it added or subtracted. Because output values are a vertical idea, it's moving vertically on the y-axis. Now look what an input value would do. Let's say I would take my, now what's this do? Wait a second. It takes an input value. X is our input. It says, right before you do anything else, I want you to add to that. Or take your input value and before you do anything else, I want you to subtract from it. Well, because X is our input axis idea, adding or subtracting to an input value before you put any sort of function onto it, or in any sort of function, it's going to affect shifting on our horizontal axis. It's a horizontal shift. Because our input axis is horizontal, and because we're affecting our input first, it's going to take an input value, it's going to alter it. It's going to say, I'm going to move you to the right or to the left. Man, I'll tell you what, in the 15 years I've been teaching now, I've taught this stuff in 60 different classes to 60 different groups of students. And I'll tell you what, this idea is the #1 missed idea when you are graphing with transformations. People really, really want this to be a shift right. It's not. They really want that to be a shift left. It's not. It's opposite of what your brain wants to make it intuitively. I'll tell you what, in parentheses, anything that happens in parentheses is almost always opposite of your intuition. It's weird, but that's the way it works. I'll explain that very well in just a second. What I want to make sure that you get right though, this is shift. This is a shift in a direction on the horizontally, and this is a shift horizontally in the correct direction. But man, you need to get your shift straight, all right? So this is a shift left, and this is a shift right. You probably see that's really easy for students to get confused. They go, I really want plus to, plus means up, and it does. Don't ever change that. Plus means up when it's outside of function, when it's affecting the output. Yes, it does. Plus does not mean right when you're affecting the input. Minus doesn't mean left when you're affecting the input. Everything in parentheses happens opposite of the way that you want it to happen. So here, this is going to, or inside of a function. So that's not a shift to the left. This will be a shift right. Why? Why is this a shift left and this a shift right? I'm going to explain it two different ways. One way is just the whole input idea. What this does, let's focus specifically on this. This says, I want you to take a number, and I want you to right when I plug it in, add 2 to it. In order to get out the same height that I would normally have got, so let's say 0. Let's say I want to get out a height of 0. If I cover up that 2 and say, in order to get a height of 0 out, I would plug in 0 because the absolute value would be 0. Now you tell me, okay, I'm going to add whatever number you give me, I'm going to add 2 to it, no matter what. So okay, now what if I wanted to get a height of 0? If I plug in 0, it's going to be a height of 2. What value would I have to plug in order to still get the same height if you're going to add 2 to everything? Well, it's not 2, because if I say 2, no, 2 plus 2 would give me a height of 4. In order to undo this sort of a adding to your input idea, I'd have to put in an input that's less than what I started with. So I'd have to put in -2 in order to get the height of 0 back. So I hope that makes sense. I'm going to explain it a different way in just a second. But if I want to get at the height of 0, I'd plug in 0 to get out 0 here. I'd have to plug in -2 to get at the height of 0, the same value that I would get out previously. Well, -2 is not to the right. -2 would be to the left. It's a shift left. The other way I can think of it is like a timeline. Let's say that the year is 2050. If it is, that's cool. You're watching this in the future. Although it would be the future for me, not for you. For you. Weird. Let's say that that's the year 2050. And here's the year 2000. And I walk into the room and I say, in the year 2050, at this time, I say I'm 50 years old. I am 50. When was I born? I was born in the year 2000. Okay. Now, that should make sense. Hopefully that makes sense to you. If it's 2050 and I'm 50 years old, which I won't be, I'll be older than that, unfortunately. And I say I'm 50 years old, you go, okay, you were born in the year 2000. Now, what if I walk into the room and say, oh, now it's still the year 2050. And I say, I'm now 48. I'm 48 years old. So it's the year 2050, and I walk into the room and I say, I'm 48 years old. I've subtracted 2 years from my age. Am I born in the year 2000? No. I subtracted 2 from my age. Am I born in the year 1998? No. I'm born in the year 2002. Even though I subtracted 2 from that time, I've moved to the right on my timeline. That's sort of what's going on. I'm subtracting 2 from my input value. It's moving me actually to the right. I know this is adding 2, I get it, but I need to understand that subtracting 2 from your input, subtracting 2 from your value is a moving to the right sort of idea on a timeline. That's what's happening here. I hope one of those two things makes sense to you. But for us, we just need to understand, I did explain it a couple of different ways, but we need to understand that adding to your input value, in order to undo the adding to an input, you would have to give me a smaller value. That's to the left. In order to undo subtracting from my input, you'd have to give me a bigger value. In order to undo that and get the same height out, that would be a shift to the right. In order to undo this adding 2 to your input, I'd have to give you smaller values so that when you add 2 to it, I'd get back the original height. That's the idea. It's an opposite of what you want it to be. So this shift, let's look at that. That's an absolute value of x plus 2. The first thing we want to understand is that absolute value gives me a v. I'm going to get a v here. The second thing to understand is that I have some key points. My key points are 1, 1, 0, 0, and -1, 1. That would be the key points of my basic absolute value of x graph. That's what absolute value of x is going to have. Now we identify that the plus 2, what that does, it takes the absolute value, it says that plus 2 is going to be an affecting of the input axis. It's not after the absolute value. It's not affecting the output. That doesn't affect the output. It says I'm affecting the input first. It says before you even look at the absolute value, I'm saying plug in a value of x, I'm going to add 2 to it. That's affecting the input. That's a horizontal shift. In fact, it's a shift left. Left 2 units. So I've looked at it, absolute value is a v. Absolute value has these key points. I've looked at my function and saying, this is inside my function. This is affecting the input, the x input. That's a horizontal idea. It's going to shift left 2. So what we're going to do, this isn't shifting up and down. There's nothing outside of that function to shift up and down. It's not that's affecting the output. So what we're going to do is we're going to say, all right, well, according to that, this would shift my graph left 2. It would not shift my graph up and down at all because there's no constant that's being added to every output value. Are you seeing how when we sort of create a new XY axis, it's given us a place where we can plot our key points. So when we shift our graph, we're basically shifting the V and just moving where that thing starts. So if we're moving this graph left 2, I can still plot the 0, 0 and the 1, 1 and the -1, 1 like I would normally get on a absolute value type of graph, but I've shifted the whole thing over 2 units to the left. Plus inside a function means to the left. I know it's not intuitive, but when we really think about it, that's what has to be the case. In order to undo the adding 2 to every input, you'd give me smaller values to get the same output. So we say, all right, let's plot our new XY axis. It's not really there, but I can use this to plot my key points and graph my absolute value. I know it's not a parabola. Do not give me a parabola. That's an absolute value graph, and we're sketching here with our transformations. I hope that that makes sense, that adding to an input is actually moving you to the left, not to the right. And you can check it with outputs if you really want to. Plug in -2. -2 plus 2 is 0. Absolute value of 0 is 0. The original absolute value would be here. That's moved us to the left. Plug in -1. -1 plus 2 is 1. Absolute value of 1 would be 1. That's the correct graph. It's just moved to the left. Are you seeing why we wouldn't want to just graph these by plugging in points? What if you just plugged in -1, 0, and 1? You'd just get a straight line. You wouldn't get this key feature, this change from decreasing to increasing, this local minimum. You wouldn't even get it unless you plugged in -2 and then -3. You might not do that if you're just plugging in values. So we really want to get a feel for what transformations actually do. This is one way to do it. Figure out your basic graph, put your key points, identify your shifts, and then graph your key points from your new XY axis. Yes, these key points aren't actually there. The points are -3, 1, -2, 0, -1, 1, but it's a good way to do it. All right, we're going to put this stuff together. I'm going to go kind of quickly through it. So I'm going to model my thinking on what our basic graph is. I'll write my key points first. What our shifts are doing. I'll move my X and my Y axis on both of these, and then we're going to graph them. So when I were looking at it, man, f of X it's based on an X cubed graph. Now some stuff has happened to it, but it's based on X cubed. That means I know I'm going to get this S curve going, sort of an S curve going up. I know that it's odd. It's an odd basic graph shape. I know my key points are 1, 1, 0, 0, and -1, -1, because it's based on that odd graph. I also know what my shifts do. So how I look at this, I look at the end first. I look at after the function's over with, after that power 3 is over with, is there anything that's added or subtracted to it? This is, yeah, this right here says that I'm shifting down 1 unit. It's after the function, it's affecting the outputs of my function, I'd shift down. This +1, that +1 is inside. Now I really want my head +1 to be to the right, but I know it's affecting the input. I know it's inside the parentheses, inside input. So I'm affecting this by adding 1 to the input. I know I want it to be the right, but I know the inside parentheses is opposite of that. So adding 1, in order to undo the adding of 1, you would have to give me a smaller value to get out the same height. So this would be a left 1. So I've identified my graph. I know I'm going to be graphing this. I've identified my key points based on the fact that it's an odd graph in our library of functions. Now I'm shifting down 1 and left 1. I'm going to draw like a new XY axis, a new location for me to graph my key points. So there's down 1. And here's left 1. So we're going to put our key points on that graph. So our key points were 1, 1, but I'm graphing it from this new XY axis. I'm kind of not focusing on the black lines, I'm focusing on my dotted lines here. So 0, 0 would be here. 1, 1 would be 1, 1. It would actually be at the old origin. And then -1, -1 would be, according to the same scale, right here. I have memorized my cubic. I know what it looks like. I know that it's this short of a curve. That's what that graph looks like. Normally, we get something that's just a sketch. We can make it a little bit better. One way to make it better is to plug in a few points that you don't know. Now, I just said don't graph this thing by plugging in points. I understand that. We didn't. We graphed a very good graph by just having our key points and shifting them. If you want to make it better to get more of a feel for what the graph really looks like, maybe plug in a value like the y-intercept. Now, we already have that here. 0, 0 is on our graph. But if you wanted to see plug in 1, where this thing actually goes, or plug in -3, it'd give you a better feel for it. Same thing here. We could be a lot more specific by saying, hey, you know what? I know what our real key features are, but if I want to find out where this crosses the y-axis, plug in 0. If I plug in 0 here, 0 plus 2 is 2. Absolute value of 2 is 2. So I know that really I'm crossing at 2. This is a little bit off. I didn't do it correctly. We can get a much better look. That's not much better. By graphing that through its actual y-intercept. Is there more? Could you do more? Could you understand that because this is even, man, stick with me here. Because this is even, I know that if this 2 units away from my axis of symmetry, why would you want to use my technique to graph? Why would you want to shift over the y-axis? It gives you explicitly your axis of symmetry when you do that. If I want to use this axis of symmetry 2 units away, I can use symmetry because it's even. 2 units away, I know it has to also go through that point. You get one for free. That's really nice to do that. You could do the same thing here. All right, so our last one, we know that this is a function that's based on a square root graph. So in your head, hopefully you're thinking square roots look like this. They're half of a parabola on its side. That's what they look like. I know my key points. My key points for square roots, there's only two of them. I know 1, 1, and 0, 0. There are no negatives that are allowed in your square roots. That means that not necessarily you can't plug in negative numbers, but I can't plug in any value that's going to give me a negative number inside. So, for instance, I can't even plug in 1 here. I can't plug in 1 because 1 minus 2 is negative 1. That'd be a problem. So we're probably not going to have anything to the left of an x value of 2. Now, it's fine because that says shift to the right, but we want to think about that right now. This is a one-sided graph. It's based on the square root. It's based on original key points of 1, 1, and 0, 0. No negative 1, 1, no negative 1, negative 1. So I understand that. I know the shape. I know my key points. Now I'm going to identify what my shifts are. So the plus 3. What's happening with that? I go from the outside in. The plus 3 says that I would take after my function and affect the outputs by adding 3. Adding 3 is going to move my outputs up. So that's a shift up 3. Now I'm going to look inside. Okay, inside my function, inside parentheses or absolute value, or inside the square root. I see a minus 2. So in my head I think, okay, minus 2 is affecting horizontal. Minus 2 is going to be to the right 2. I'm going to subtract 2 from every input. In order to undo that and get the same height out I originally would, so where my graph is, the same height but moved over somewhere, I would have to give me bigger numbers. Those are to the right, bigger numbers to the right. So this would be right 2. So I've identified my shape, my key points, what's happening to those key points, and now I'm going to graph it. So on our graph I go, okay, I'm going to shift up 3. That's going to shift us up 3 spots. I'm going to shift right 2. That's going to shift us over, and allow me to shift an axis over 2 spots. So up 3, right 2. Even though that's not actually on your graph, and even though my key points when I shift them are going to be different points on your graph, it's a really nice way to get where this graph is, what this graph looks like. So I would look at it and go, okay, here's my new XY axis. If I graph these key points from this new XY axis, I'd have 0, 0. According to the same scale on my graph, I'd have 1, 1. Now the actual point's 3, 4. You didn't know that. This is not really here, but it lets me identify exactly where my graph is. I know my shape. I know I'm not going to put a V. It's not absolute value. I'm not going to put a parabola. It's not a parabola. This is a square root type of graph. That's why it's so important to memorize the shapes of these graphs from your library of functions. If you want to be a little bit more specific, you might plug in a value, probably not 4. If I plug in 3, I know I'm going to get that value. 4, I get the square root of 2. That's kind of hard to deal with. So maybe something like, let's see, if I wanted to get out 4, I'd plug in something like 6. Plug in 6. 6 minus 4 would give you 2. Sorry, 6 minus 2 would give you 4. Square root of 4 is 2. And then add 3, you get 5. And you could find a couple other values if you wanted to be better, get a better graph. But for sketching, this is what I need you to know. I need you to understand the shapes of the graphs on the basis of what I've given you. I need to understand the key points on being even or odd. And then I need you to understand what these shifts are doing. After the function, plus means up, minus means down. Within the function, plus means left and minus means right. I'm putting those together right now. I'm going to come back with how to affect your outputs as far as stretching them and compressing them, and then we'll talk about how to reflect them. Let's continue. So the last couple that we have, last 3 that we have to deal with is how to take a graph and stretch it out vertically or compress it vertically, how to stretch it out horizontally, compress it horizontally, and how to reflect it both across the x-axis and across the y-axis. So we'll talk about those kind of 4 transformations. We'll talk about how this one really, almost always in at least polynomial-driven functions, you can change it into a vertical stretch compression. And so we'll really focus on vertical stretches and compressions and then our reflections. Let's talk about the vertical stretch and compression. So imagine that you take an input, you don't mess with it. Look at what you're doing. You're not messing with the input. You're saying, take my input, plug it into a function that's going to give me an output value. F of x stands for an output value of some function. So take your output value, now multiply your output value, not your input value, multiply your output value by some sort of number. What's going to happen? Let's say your input values were something like, I don't know, 1, 1, 0, 0, and negative 1, 1, like the key points for x squared. Now take those and multiply your not input. This is doing nothing to your input value. That happens over here. This is doing nothing to your input value. This says take your output value and multiply by a number. What's going to happen? Your input values aren't going to change. So for the same input values, your output values will start growing or shrinking, depending on whether you multiply by a number greater than 1 or less than 1. So what the vertical stretch and compression does, it says you're taking your output value and you're multiplying by a number. It's going to leave your inputs alone. It's going to stretch it if the number is more than 1. Taking your output value times 2, times 3, times 1.5, times some fraction greater than 1. It's going to take those and it's a multiplier. Taking your output and multiply them. It's not a shift. It's not moving the whole graph. It's taking the graph and growing your outputs. Or if you multiply by numbers less than 1, 1/3, 5/7, 1/2, taking your output values and shrinking them. That's what's happening here. So for our A values greater than 1, you're going to get what's called a vertical stretch. It's going to take those output values and it's going to multiply them so they get bigger. What that's going to do, it's going to start making your graph look more narrow. Imagine, like I'm 6 feet tall, so if I stayed my same weight and I gained like 8 inches, well, I'm going to get pretty tall, but I'm also going to get pretty thin. So I'm going to go, whoa, that's gonna make me appear narrower and taller. A vertical stretch is a narrow sort of idea. I'm also going to talk about this in a minute because I don't want there to be suspense. A vertical stretch is a horizontal compression. A vertical compression is a horizontal stretch. If I was 6 feet, I'm 6 feet tall. If I shrunk 8 inches and stayed my same weight, I'm going to get wider. There's no way I'm not going to be wider. That's what happens with these vertical sort of stretch compression idea. So with our values greater than 1, we're multiplying our outputs. It's not an input idea, it's an output idea. I'm multiplying them by numbers that are making them bigger. I'm stretching out my outputs. That's a stretch and it's going to be more narrow. For numbers less than 1, that's shrinking. That's saying take your output and give me fractions of them. So I'm going to take my output values with my inputs being the same and make them smaller. That's going to shrink it. That's a compression. And that will make the graph appear more wide. So let's go ahead and let's talk about this one. Look at what this says. Look what it does to the output. This says I have an x squared type of graph. That's my basic graph shape. I've done my key points, 1, 1, 0, 0, -1, -1. Now this says these are all your outputs for x squared. Your inputs are not affected. All your outputs for x squared would be plug in a number and square it. Now take all those outputs and multiply times 2. Now what can we do? Why in the world would Leonard want you to learn key points for something? Because if you're taking your key points and all you're doing is affecting the output by multiplying it by 2, then why don't we just take our output and multiply the outputs of our key points by 2? So what this 2 does, it really does take this and multiply your outputs, not your inputs. So you'd still get 1, but 1 times 2 is 2. 0, 0 times 0 is 0. Negative 1, 1, well, negative 1 would say the same, but 1 times 2 gives you 2. Those are your new outputs for this graph. Now, we did not shift up. We didn't shift down. There's no plus after here, no minus after here, no plus in here affecting the input, no minus in here affecting the input. So really, we still have 0, 0. But now we have, instead of 1, 1, this has affected the output values, not the input values. There's nothing in here affecting the input. There's nothing in here affecting the input. Inputs are the same, but affect your output values by multiplying by 2. That's why I wanted you to learn the basic graph shapes and their key points so that we can start affecting the outputs and later affecting the inputs. This is affect your outputs by multiplying by 2. So instead of 1, 1, you now have 1, 2. 0, 0 is the same, negative 1, comma 2. This has taken your original parabola and made it skinnier, made it more narrow. It's stretched it out vertically. That's what's going on. Now, how about the next one? What about 1/2 x to the third? So we're looking at going, all right, this is an x cubed graph. This is an odd graph. This has key points of 1, 1, 0, 0, and negative 1, negative 1. But what does this do? There's nothing added or subtracted, therefore there's no vertical shift. There's nothing added or subtracted inside the function, no horizontal shift. This says take every output, can't do it that way, take every output of your x to the third power and multiply it by 1/2. Don't affect the inputs, just take the output values and multiply them by 1/2. That would take the output values and that would cut them in half. So 0, 0, not the inputs, but 0, 0, 1, 1, negative 1, 1, and affecting the outputs only. 0, 0 would still be 0, 0. 1, 1 would still have an input value of 1. This is not affecting the inputs, but it'd have an output value of 1/2. Negative 1, negative 1 would still have an input value of negative 1, but have an output value of negative 1/2. It's cut all of those output values in half. Do you see how it's going to squish it? It's going to squish it down. That's what's happening here. In the future, what's going to happen is we're going to do two transformations at once. This will be the next video when we just practice all this stuff. If I put a negative sign out front, doesn't look very good, but if that's a negative sign out front, then that would affect the outputs by changing the sign as well. So we can do both a vertical stretch or compression, and we can do reflections about the x-axis at the same time. So I want you to watch out for that in the next video. That's what we're going to be doing. So let's graph it. We did not shift up or down. We did not shift left or right. We took our key points, we affected our outputs by cutting them in half. We still have 0, 0, but now instead of 1, 1, we cut the output in half. Instead of negative 1, negative 1, we cut the output in half. So this is going to be a much shrunken sort of a graph as far as a vertical compression. We can plug in a couple other points if we want to be a little bit more accurate, but notice how it took our original S-curve and went, sort of shrunk it down, it compressed it. Also, it made it a little bit wider because it compressed it. This made this graph narrow because we stretched it. I hope that makes sense to you, that we still have some key points, but then when we talk about a vertical stretch and compression, we're affecting the output only. We're growing it if the number in front is more than 1, and we're shrinking it or compressing it if our A is less than 1, fractions of your outputs. Now, how about horizontal stretch and compression? I'm not going to talk a whole lot about this, just one thing. It's very, very common that a horizontal stretch or compression can be changed into a vertical stretch or compression. Almost always with the stuff we deal with. When we get to trigonometry, no, but there's sort of a different way that we're going to approach it. So I'll get there when we get to those videos way, way, way in the future. For right now, what I would like you to understand is that when we talk about a horizontal stretch or compression, I mentioned this just a little while ago, that virtually everything inside parentheses is opposite of your intuition. So here's what's going to happen. If you have a number greater than 1, so your A here, if your A is greater than 1, what that's going to do, that's going to give you a horizontal compression, not a horizontal stretch. It's opposite of what you kind of want it to be. Numbers greater than 1 are a horizontal compression. Numbers less than 1 are a horizontal stretch. Why? Why in the world would that be the case? I said something a while back. It goes into this. If I talk about a vertical stretch, it would be a horizontal compression. When I stretch something out, it's going to make it appear more narrow. It's going to compress it horizontally. When I squish something down vertically, it's going to stretch it out horizontally. Those things work hand in hand. I'm going to prove it to you right now. So if I have f of x equals 3x quantity squared, that would say what this is going to do, this would compress your graph. That's a parabola. It would compress your graph horizontally. Well, isn't that the same thing as 9x squared? Go, yeah, well, that's a stretch. Yes, it is. It's a stretch vertically. X squared, and I take every output and multiply it by 9, that's going to go, it's going to make it much more narrow. A horizontal compression, A is greater than 1 here, is a vertical stretch. Do you see it? Do you see how that makes sense? If I had 1/2, it would be 1/2 squared would be 1/4. That would be a vertical compression giving us a horizontal stretch. They work hand in hand. Most of the time, we can change horizontal stretches and compressions into vertical compressions and stretches respectively. That's what we can do with it. If you don't want to do that, you're multiplying your input. You'd still get the same exact points, just doing it a slightly different way. That's what I'm going to leave it at. I'm going to tell you that horizontal compressions and stretches, we're going to change them into vertical, doing the same exact thing right there. Now, last one, reflections. In the next video, we practice all the stuff put together. What reflections do is they change the sign of either your output or your input. So let's think about this. Let's say that I give you a function and you put something into it. It gives you an output and they go, no, change the sign. Well, what's that going to do? It says, I want you to change the sign of your y value. It literally says this in English. It says, look at your y value. Your y value is based on f of x, but I want you to take the original output and now change the sign. So for something that would have a y value normally that's positive, you're going to give me a negative. For something that has a y value that's negative, normally you'd give me a positive. So you're taking your sign of your output. Sign of your output is a vertical idea, and I would change the sign. Change the sign, or change the sign, change the sign. What's that doing? Well, that's taking your graph and reflecting it vertically, reflecting it about, not the y-axis, but the x-axis. Changing the output sign puts it on the opposite side of the x-axis, because the x-axis marks where your outputs change sign, doesn't it? So the x-axis floats at y equals 0. Above the x-axis are positive outputs, and below are negative outputs. So if I start changing the sign of that, positive becomes negative and negative becomes positive, it's reflecting it vertically. That's a reflection about the x-axis. What happens if we affect the sign of our inputs? It's not nearly as common as our outputs, but imagine I say, I want you to plug in 5. You go, okay, -5. Oh man, no, I said 5. -5. Fine, -5. You go, +5. You start changing out the inputs on me. Well, if I change an input sign, then an input sign says if I would normally plug in 5 and I'm changing the sign to give me -5, or plug in -2 and now you change the sign to give me +2, that's what that would do. It would affect the input before I even got to the function. What that's going to do is affect the side of the y-axis that you are on. This is a reflection about the y-axis. Now, like always, I need you to know what the shape is of the graph that we're talking about. So I need you to know that this cube root function is normally this sort of an S curve. It's like the cube root. It's like the power 3 function flipped on its side. So that's what that's going to look like. I'm going to be graphing that, but let's understand it. This right here, this basic graph shape has key points. Everything comes back to shape and key points of 1, 1, 0, 0, and -1, -1. That's the key points for this graph. Now, what's the negative do? Does the negative affect the input? Does the negative affect the output? Well, it's not next to the input. It's not affecting the input. I'm telling you, you're telling me I'm going to plug in the same input, no problem. So plug in 1 or 0 or -1, no problem. But this says take whatever the output value is and change the sign. So take your key points, take whatever the output values are, and change the sign. Not the 1, not the 0, not the -1 as far as inputs, but the 1 for an output becomes -1. 0 does not change. -1 for the input, no problem, but change this. That's what this says. It says change the sign of your output. Change the sign of your output of your original function. 1 becomes -1, 0 stays 0, -1 becomes +1. What's that done? That has not changed the input, but it's given you an opposite output for that input. So at normally being at 1, 1, now you're at 1, -1. Notice what it did. Take your output value, it just flipped it over the x-axis. 0, 0 didn't change. It's not going to change for any of these. -1, -1 is what you normally had. It's to change your output. -1, don't change the input. -1, +1. So what's going on? We would normally have this graph. But now it has reflected it about the x-axis. You go, wait a minute. That looks a whole lot like it reflected about the y-axis. You can view it two different ways. Notice if I took this and moved this negative inside, cube root of negative x is the same thing as a negative cube root of x because that is an odd function. That's the way that would work. So you can view it two different ways, but the way that we talked about it, what this would do, what that negative does, that negative would affect the outputs. It would flip the output over the other side of the x-axis. That's what that reflection does for you. And I would want a student to understand what that transformation is. We would say this transformation, there's no vertical shift, there's no horizontal shift, there's a reflection about the x-axis. That's what's going on here. Okay, this last one. What happens about reflecting over the y-axis? This says take your input and change the sign. All right, my input value is x. Now change the sign. Give me a negative x. So, well, let's see, a square root. Our key points are 1, 1, and 0, 0. It's neither even nor is it odd. It's neither. It has only two key points that we really focus on. So it says, now I want you to take your input values, and I want you to change your input values, but leave your outputs alone. So this would give us instead of 1, 1, it'd be negative 1, 1. Instead of 0, 0, oh, it'd still be 0, 0. So going from our graph, our normal graph would look like this. Our normal graph would have a point at 0, 0, and it would have a point at positive 1, 1. And it would look like this. That half of the parabola on its side. If I say, now switch the sign of your inputs. Leave your output values alone. Switch the sign of your inputs. Then instead of positive 1, 1, I'd have negative 1, but I'd still have an output of 1. And 0, 0 is still there. That's a reflection about the y-axis. That is what's going on. I hope that that makes sense. I hope that I've explained it in such a way that you understand that what a vertical stretch is affecting the output and leaving the input alone. By multiplying the output by some number. Numbers bigger than 1, take a number, multiply it by something bigger than 1. It's going to grow it. Take a number, multiply it by something less than 1. It's going to shrink it. That's what's happening here. When we talk about reflections, we're talking about take an output and multiply by an opposite sign. So change the sign. It's going to take an output value and reflect about the x-axis. Take an input value and multiply it by an opposite sign. You're going to take an input and put it on the other side of the y-axis. We are going to put all these things together in the next video and talk about vertical shifts and horizontal shifts and stretches, compressions, and reflections all at the same time and do a good job of explaining what in the world they do. We'll talk about shifting our x-axis and y-axis using our key points, affecting the outputs or even the inputs of our key points, and seeing what that does as far as stretching, compressing, and reflecting. Hope that makes sense. I'll see you for the next video.